Let's continue our lesson. Yesterday we started with work. We talked about work and work of gravity. Today we want to talk about work of spring. Work of a spring. We said before that spring has what? Elastic potential energy, because the spring can be compressed and can be stretched, and any object can be compressed or stretched. This object has elastic potential energy. Okay, the work of a spring is done when a spring is stretched or compressed through a displacement x. Okay, the work done by a spring is positive when the spring is released and moves to restore its original unstretched or uncompressed length, because force and displacement are in the same direction. Look here to understand. Now we said before that we have something we call it force of spring. When do we have this force? When you compress a spring, a force appears. This force, its opposite, we said the name of it is a restoring force. It's opposite to the applied force, because this force, from its name, it's a restoring force. It wants to send the spring back to the unstretched or uncompressed length, to the equilibrium position. That's why always the restoring force is opposite to the applied force. If you are compressing the spring, here for example, while you are compressing the spring, the restoring force is opposite to the direction of motion. When you remove your hand, now I compressed the spring, then I release the box, or I removed my hand. So what will happen to the motion? The object will move, and the spring will move with the object, and also the force of spring is in the same direction as motion. So in this case, the force is what of spring is positive, because force and displacement in the same direction. Force of spring and displacement in the same direction. So work of spring is positive. But in the first case, while pushing the spring, compressing the spring, the object is moving to the right. The restoring force is to the left. So in this case, we say that the force of spring is what? Negative, because it's opposite to the direction of motion of the object. Okay? The work done on a spring by an external applied force is equal to the work done by the spring when it is released and moves to restore to equilibrium. Here's the formula to find work done by a spring. It's the change in what? Half kx elastic potential energy. So work of spring, it's elastic potential energy final minus elastic potential energy initial. When the spring at the end, after I compress it or stretch it, and the initial or the equilibrium position, it depends on the case. Sometimes the compressed or stretched the beginning, sometimes initial, sometimes it is final. So this is the formula to find the work done by spring. It's the same as elastic potential energy. We just add what change. It's for the displacement, the change and displacement. Let's see this example together to see how to solve the questions about work of spring. 4 kilogram mass is attached to a spring with a spring constant 20 newtons per meter, K 20, mass 4. The mass is lowered 0.5 meters to equilibrium, where it remains at rest. Equilibrium, we know that it means at rest. How much work was done stretching the spring? Direct. Write the givens, then think. They are asking for the work done by spring. Write the formula. Work of spring equals change of half kx squared. First of all, we write the formula. Second, we say that what's the meaning of this formula change? It means half kx final squared, half kx initial squared. Then The spring was not stretched initially, so x initial is 0. It was equilibrium. So we substitute in the formula half times k, spring constant 20, times x final. Here is it. They gave it to you direct. You remember before in some questions we said you have to subtract the initial length and final length. Here they gave you the x direct. They said the mass is lowered 0.5 meters to equilibrium. So it moved 0.5 meters. Okay? So this is x direct. It's not the final length. It is x final. The final x 0.5 meters, okay, minus 0, because here we said x initial is 0. We don't have any displacement at the beginning. It's equilibrium. So the answer is what? 2.5 joules. What is 2.5 joules? It's the work done by a spring. Okay, this is how we solve questions about work of spring. Is it clear? Let's continue. Interpreting a force displacement graph. Again and again. Graph. Always we have graphs in physics. Look at this graph. This graph, the name of it is what? Force displacement graph. You remember, how do we name graphs? We just say the name of the y-axis and the x-axis. Force versus displacement graph. We look at the unit. Force is in Newton, displacement in meter. Okay. What is the significance of the slope? Two important words. We took them before. Significance of slope. First of all, slope, what does it mean? Slope is the change of y over the change of x. Delta y over delta x. This is the meaning of slope. Here, I don't want you to give me an answer or a magnitude. They want you to say the slope, it represents what? When I ask what's the significance, it means it represents what? And when you measure the slope, what is this? What is this number in E2? To what? Speed, acceleration, force, displacement. This is the meaning of what is the significance. To know the significance, no need to memorize. I told you always in graphs, what do? You say slope is what? Delta y over delta x. What do we have on y? We have force. So it's force over displacement. So you think, what do we have a formula that has force over displacement? Force over displacement, it is F over X. What a formula has F over X? Remember, it's not F over X, but we have a formula is what? Force equals K times X. So, if I put K on a side, in the other side, what I will have? Here is the formula. Force, restoring force, equals K times X. So, F over X equals what? K. So when you find the slope, and the unit is what? Newton per meter, and yes, that's true. The unit for spring constant is Newton per meter. So the significance of slope here is what? Spring constant. So now you have to put in your mind, when you have a force versus displacement graph, the significance is what? Spring constant, Newton per meter. The second question. What is the significance for the area under the graph? Area under the graph, significance. Okay, how to find area under the graph? You look at what I have. I have rectangle and triangle. Let's talk about this side. Rectangle, how do we find the area for rectangle? Base times height. So area under the graph equals base times height. What do we have in the base? Displacement. What do we have here? Force. So displacement times force. So what is this? What is the formula? What is the unit? Newton times meter. Newton times meter is the unit of what? It's the unit of work. Work equals force times displacement. Here's the formula. Force times displacement, the formula for work. So area under the graph represents work. Okay? Good. Let's see this example to understand how to use graphs to find work or spring constant. A variable force acts on a 5 kilogram mass, displacing the mass 8 meters. The force and displacement are graphed above. Determine the work done on the mass by the variable force. They want you to find work. You have here you have this graph. What do? You have to remember that work in a force displacement graph is what? Area under the graph. So direct, you just write area under the graph. It is what? You have a triangle, half times height, half times base times height. So half times the height, which is 4, and the base, which is 8. So the answer is 16 joules. The last thing we're going to talk about today is work kinetic energy theorem. The work kinetic energy theorem states that work is equal to the change in kinetic energy. So, we said that before. I told you, for example, if there is an object at rest. Now this object has zero kinetic energy. When you start pushing the object, what you are doing, you are increasing the kinetic energy. You are changing the kinetic energy from 0, for example, to 10, from 0 to 5. So while you are, at the same time, you are doing work on that object, you are applying a force and distance, so there is work and there is a change in kinetic energy. When one or more unbalanced forces act on a mass, the mass will accelerate, changing in both speed and kinetic energy. Several forms of work may be present, maybe work of friction, work of gravity, work of spring, or work of applied force, and can be calculated. The net work done on the mass will be equal to the change in kinetic energy. So not only one of the work. Now we know while you are pushing the book on the table, there are two forces acting on the book. Force, applied force from your hand, and work of force of friction. Now, so you have to work on the object at this time. So you have the net, you find the net work first, then you substitute in the formula and you solve it with the change in kinetic energy. So the formula is what? Work net equals the change in kinetic energy. What does mean change in kinetic energy? Kinetic energy. Kinetic energy final minus kinetic energy initial, which is half mv final squared minus half mv initial squared. This formula is very, very important. Work kinetic energy theorem. Okay? Don't forget it. We're going to use it a lot. How do we use it? If they give you the work, sometimes they give you the work in the question, the network, and they give you the mass. And they ask you for V final or V initial. So direct. Don't think which formula I have to use. You have to use this formula. This is the only formula that rate work and energy together. Okay? Let's see an example. A 2 kilogram mass moving at 4 meters per second is acted upon by a force which does 20 joules of work on the mass. Determine the final speed of the object. They want you to find the final speed. The initial speed is given, the mass is given, work is given. So what you are going to use? Work kinetic energy theorem. That's it. Work net equals change in kinetic energy, kinetic final minus kinetic initial. You write the formula, then you substitute. 20 joule is the work, here is it. Half times mass, 2 kilogram, V final squared, unknown, I want to find it, minus half times 2 mass, kilogram, V initial squared, is given in the question, 4 squared. So the answer for V final is what? 6 meter per second. That's all for today. I hope that everything is clear.